Okay. Yeah. So then let us say, so you can tell me the first question. So problem 1 or just question 1. So the question number 1, it's up to you to choose and tell me. Okay, right. So let's do that. Yeah. So we had a triangle, and then what were the lines like? There were some ratios I had given. Maybe if you know, tell me the ratios. Mhm. Mhm. And what was the ratio? So just draw according. So this is 3:1. Okay. And and what was the ratio? Okay. Right. Yeah, and that we kind of could figure it out. Yeah. Okay. So what is that? Let me mark this P. Okay, yeah, ABD would be 3/4. So that's like already clear from the ratios. Okay, but let's just still write it. ABD is, so this is clear from the ratio, right? And yeah, so those are there. So let's assume that ABC area is 1. Okay, so then yeah, then BEC area was half, and similarly AFC area is 1/4. Right, and the goal is to find area of the small of each of the smaller triangles. Okay, so find find, let's say if I ask find BPD. So let's think about, by the way, are both of you comfortable with the Ceva's theorem? Yeah. Okay. Yeah. Pragadish, are you okay with the theorem? If 3 lines are concurrent, then the product of the ratio was 1. Okay. So I'll just tell you this, just say the theorem once again. You see, if we have 3 lines which are concurrent, then what can we say? So then we say that BD by DC. Okay, so we are going cyclically like this. BD by DC, and then we are saying CE by EA, and AF by FP is 1. That's all. We will see the reverse is also true. If the ratio, so if there are 3 lines like this, if just 3 lines are there, okay, AD, BE, and CF, and if the product of the ratios turn out to be 1, then the 3 lines are also concurrent. We will see that. That will give us maybe our first tool, okay, to show that 3 lines are passing through the same point. Otherwise, we don't really have many tools to do that. Okay, but we'll see that later. Yeah, so let's focus on the special question maybe. What is the area of BPD? Let's try to see if we can figure this out. Yes, yeah, so let's see what you have done. Oh, so this is, I'm just calling this P. Okay, let me call it O. Actually, O is not a bad notation. Okay. So you are saying, okay, you kind of broke up the triangle. Okay. So I'm not putting the box now. I mean, it's, okay, let's put actually here, let's put, and then we have BOF. Okay. BDO is 3 times. So this is I think this is a very crucial observation. Okay, so let me highlight this thing. BOD or BDO, so this is 3 times ODC. So let me confirm this. Pragati, do you see this? So there is this small triangle which I want you to look at. It is, you see, yes, exactly. So it is just the same principle being applied. Okay. Definitely. Hmm. Yeah. Instead of FOB with 3. Okay. Okay. So can I do one thing? Just put some variable names. Okay. So I'll ODC, I'm going to call X. Otherwise, you have to just repeatedly write the same thing again and again, right? So I'll call ODC equal to X. Let me call EOC equal to Y. Okay. And let's call AOF equal to Z. Fine. Okay. Now in this, we just do some replacement. So AOF is the Z. And BOF, yes, plus 3Z. 3x. The way I have named it, it will be 3x, right? Is that right? This is x, so it's 3x. Okay, once again, I just close this. One tab is open, which I should close. Okay, 3x, and this is 3. Okay, then right. So the point is that from here you do this similar kind of calculations, and you should get the answer, right? You have to just have set up variables. So this is so again, let's do it. So ADC, just break up ADC. ADC is equal to ODC, which is x, OEC, which is y, and then we have AOE, which is again same. So this is, so you have another equation. I mean, it's not hard to get more equations from here. Hmm. Okay, but so and let's do the calculations. I think there is a good merit in doing it. Let's do it again. If you have already done it, you can match it with this. Okay. Yeah, because there is a certain new thing which we learn. So let's do the calculations. Otherwise, I could have just left it. So what is the other triangle? Do we need we need one more equation, right? Okay. So Pragadish, can you help us with finding one more equation like this? So just choose some other triangle and as y, much more helpful. Okay, anyways, I think that's minor point, but yeah. And let me then label everything, right? 3x and 3z. Yeah, fine. So you see, you can just set up one more equation, right? So like this thing you can say, right? This thing is half, right? ABE is half. Any equation you can set up. There is nothing special. So you see that ABE is half, okay, and that is 4z plus y. Pragdish, is it okay? Okay. So you see, this is just, I mean, you could have taken something else also, but it's just these three equations I'm getting. I mean, if you get some fourth equation, it will not be actually anything new. It will be coming from these three only. But so you can get any equations. Now we can just work this out. So please solve this for me and tell me what comes. But what is x, y, and z? Are we getting? Okay, you can just put this value, right? If 3 times y is 2 times x, then we can put it in this equation. Yeah, and you can put it in anything. Yeah, that's not a problem. So this is half. I'm just putting it here. 4y plus 2x, same thing. So then we get 5y, right? Just putting it here. And so then y comes out to be 1 by 10. Sorry, y comes out to be 1 by 10, right? Okay, let's see then. So let me actually do it. Let's actually do it. So let's get rid of the y. Okay, so y is equal to. So 1 minute. Let me remove certain things, not make it a mess, because this calculations will. I think if I am able to do this nicely, in the end, explain this nicely, you will see something very nice from here. Said. And so you can replace the y. So 2y is equal to 1 minus 8z. So I'll replace that in this equation. Okay, so this equation will become the 2y. I'm replacing that by 1 minus 4z, 1 minus 8z. So 1 minus 8z. Yes, just from here. And this is coming from this one. Okay, so y is equal to half minus 4z. So this is just calculations. So, but yeah, we have to do it. 3 by 4. So 8z minus x is 3 by 4. Okay. Okay, and but then we have. Okay. 4x plus y is half. Yeah, that is better. Yeah, 4x plus y is half. Yeah, basically we can solve f for x and y from here. Yeah, it's much easier. Okay, let's do it. So 1 equals to 8y, but I'm just checking it. So 8x plus 2y. And so you just equate these two things. So then we get 8x plus 2y, 8y plus 4x. So we get 6y equals to 4x. Yeah, so 2x is equal to 3y was just correct, right? Yeah. So, yeah. Yeah. I mean, yes, yeah. So 4x. So right. So basically, there are so many ways to do this. So yeah, 4x. This 4x becomes 6y, right? There are just many ways to do this. Okay, so 6y plus y. So the 4x is equal to 6y, and 6y plus y is half. Uh-huh. Yeah, that is a much better. I got it. Yes, yes, that's a much better. Uh-huh. So see, there are some good ways to do it, or if you are not being smart like me, then you will end up solving a big equation. Yeah, so you can do it in so many ways. Okay, so it's good that you guys are finding other different interesting ways, so that you know that solving equations is not just a machinery thing, but it's there are you can make better things if you do properly. Okay, so then y is 1 by 14, and then x is equal to 3 by 28. Okay, and this is coming because I just chose the numbers arbitrarily, so we are not getting any good things, but it's fine. This is how you can get in exams also. That doesn't matter. I mean, we are able to do this. That's all. And this is also Z. Wonderful. Wonderful. Okay, so we found all of them. Okay, whether this was the best way to do it, I don't know, but we found all the ratios. So let me not go into doing this in a better way and so on, because we did it fine. Let's move on. But I wanted to make an observation from here, which I want to make, because that is going to be crucial. Yeah, 1 minute. Yeah, let's get into that. There are two ways I can go from here. I can tell you how this technique that we have used will give another proof of Ceva's theorem. Okay, but let's not do that. We already have a proof, and we kind of our own proof we did, so no problem. We don't need another proof now. It's not that important. But now, can any one of you tell me what is AO by OD? So there's nothing to do actually. You can just, there's a good quick way, but try do it. Okay, so try to use the areas. We know all the areas, so it should be very easy to find AO by OD. I mean, we've actually already found it. It's already there in front of us. So how are you getting? Yes, right. This AO by OD, so AO by OD is nothing, right? It is nothing but the ratio of the areas. You can look on the left side, ABO and OBD, or you can look on the right side also. It's up to you. It's not 1 because there is 3x and there is 4x. So it's 3:4. But you get it, or 4:3, something. But you see, you've got the idea. I mean, that's what it is. Yeah. So it's just 4 and this is this. So basically, this is equal to both the ratios. Okay, AOC and ODC and so on. So we're seeing a very, very fruitful interplay, right, between ratios and areas. Okay, one seems to help the other, and it goes both ways. Okay, wonderful. Okay, so I mean, we have found this AO by OD, and you would remember that in some of the problems we had to find such ratios, and we found it by a nice way, but very tedious way, right? We drew some parallelograms and so on. Sorry, I mean parallel lines and so on, and then we found, right? But this seems to tell us like a, let's see, like a better way. What I would like to say from here is, okay, now you try to look at the triangle ADC. So now we have some tools to deal with concurrency. Like when concurrency is given, we are able to get some ratios, and we will see how those ratios also imply concurrency. But now we want to deal with collinearity. These two things always occur together. When you have some congruency situation, you have some collinearity and vice versa. They'll always appear in the same picture. If one of them is there, the other will be there. But collinearity means when 3 points are on the same line. Okay, or basically when you have a triangle and you have a line passing through it, some ratios are given. You would like to find the remaining ratio. Okay, right. By using that some line is passing through, basically some concurrent, some collinear situation is there. So we will try to see that from here. So here you try to focus on, let's do it with a thick pen. You try to focus on this triangle ADC. Okay. ADC is a triangle, and you can see that there is a line BO which is passing, a BOE. Okay. So this is like the transversal, okay, that is passing. So basically you can say that E, O, and B are on the same straight line. Okay. We would like to connect the ratios once again. Okay. What ratios are we interested in? Obviously, we have AE by EC is one ratio. We have AO by OD is another ratio. And then you have another ratio, which is basically this line that is passing through the sides of the triangle. So E is passing through AC, it's cutting AC into AE and EC. It's the same line is passing through AD at the point O. It's cutting it into AO and OD. But then when it is passing through B, that is really not on DC, but it's on the extension. It has to be, right? I mean, if you take a triangle and you pass a line, I mean, all three intersections cannot be on the side. One has to be on the extension of the side. Okay, so B is on the extension of DC. But then what should we say as the ratio? B divides DC into, well, we will say BD by DC. Sorry, BD by BC. Fair enough. Yeah, we will say BD by BC. That's the way to make sense of it, right? B would usually be inside the, but now it's outside, not a problem. And points and things can go outside, ortho. The altitudes can intersect outside the triangle. Circumcenter might end up being outside the triangle sometimes. So these things happen. We want to see a connection between these three ratios. Okay, let us see. So AE by EC is 1. And AO by OD, we've kind of found it's 4 by 3. Can anybody also tell me what is BD by DC? Sorry, BD by BC, not BD by DC. Okay, because B is the thing that is, if B would have been here somewhere, you would have said DB by BD by BC, right? So we are going to keep that thing, BD by BC. So what is BD by BC? Yes, it is 3/4. So do you again see something interesting? The multiplication is once again 1. Now, is this a coincidence? Okay, the 3 lines are coincident at a point, and these 3 are collinear. Is this a coincidence that the product is again 1? So let us see. Let us try to see this in a different context and see if it's a coincidence or not. So then we will. So I'll erase this thing. So we are coming towards another theorem, which is kind of coming from Ceva's theorem. It's called Menelaus theorem. Usually it's presented as a different thing, and it just said that they are duals. But we are trying to see that they are both actually, one can prove one from the other. Because you see, from the Ceva's theorem only we found all these things, right? And from here we are finding all the ratios of the sides also. I mean, of the AO by OD and so on. I mean, how about we look at it from different perspective? We take this triangle ABD, and again you look at the things, and this time you look at this. This is called the transversal. I mean, it's just obvious name, transverse cutting. So we have a triangle and we have a line that is cutting the sides of the triangle. Okay, intersecting them at. I'm just saying this for formality, kind of, at F, O, and C. Just to say it clearly. Once again, what are the ratios that we should be interested in? So someone tell me, what are the ratios we should be interested in this setup? Yeah, so in the setup of when ABD is a triangle and FOC is a line, like earlier we had ADC as a triangle and we had BOE as the line, which is cutting, right? And then there were some ratios which we kind of labeled. So these are the ratios in which the line cuts a triangle. But in this case, the triangle is ABD and the line is FOC. So what are the ratios that we should be interested in? Right. And again, AO by OD, right? And this time C intersects BD, kind of, but intersects. Yes, exactly, right? CD by. So once again, can you guys check what these ratios are? And well, we already know them actually. A by B is 1 by 3. AO by OD, we very well know, 4 by 3. And CD by BC is 1:4. Wait, no. So CD by CB is 1:4. Right. So do you see anything again interesting about these ratios? You see, the product is again 1, but just that we have to flip one of the ratios. And that is happening because we are not labeling things cyclically. Okay, last time we got saved because this was 1, so it didn't matter. But if you label things cyclically, then collinearity condition also gives you a ratio. Gives you some ratios whose product is 1. Okay, this is now clear to us, isn't it? I mean, two things cannot just be happening by luck, by chance, right? Okay, so the collinearity also gives special ratios. Concurrency gives special ratios, we saw, but collinearity also gives special ratios. We have kind of discovered that. But again, just to be formal, let me state it. Okay, it's called the Menelaus Theorem. So, but you see how we kind of smoothly went from collinearity to concurrency to collinearity, right? With areas and ratios in between. I didn't introduce it separately as a, just through these things you kind of came. And you can already see that these are going to be very important tools in calculations, at least, in finding some strange ratios and areas and so on. And they have theoretical importance. So I'll just put it in this only. I'll remove some things and put it. So we don't need this per se. I'm just removing these things now. ABC. So you have a triangle and you have a line that is cutting the triangle. Okay. You have this line which is cutting the triangle. And we would like to say that the product of the ratios is 1. What ratios? Obviously just go cyclically. So the line is cutting the triangle and cutting it at E, O, and maybe F. And then what is the product of the ratios? So it's obviously CE. You go cyclically, so CE and EA, right? And then we go AO and OB, right? Yeah, right. So we should go. Now, what should be the last ratio? EB, or you say FB. CB. No, not CB. We want to understand what is the ratio in which F divides BC, right? So CB will not come. So see, B is not what is dividing the line, right? See, it is F. It is F which is dividing BC. Well, externally dividing. It's not really in the traditional sense, but just like we did earlier, right? So we need to look at the ratio with respect to this. So FB, we'll say FB by FC. Okay. Now you may say, well, this is not really fitting in the cyclic, whatever, I'm not understanding. So you can just say that, well, you can kind of first, when you want to look at the side AC, then you can look at it from here, and then you can take the left side and then the right side. So if you choose a convention, you want to do the left side first or right side first. If you take the left side first, if you're looking at this, then this, I mean, it's up to you, but this becomes a left and this becomes a right. Then when you want to look at how to write which one to write, AO or OB, what order and to write it. So basically my point is that when you come to the side AB, then you just look at AB and again you go left, right. Once again, then obviously AO will be left and OB will be right. Yeah, from this perspective. And that's why I've written AO by OB. Now you come here and you see, and again left, right. So left is what? FB, because B is to the left, right? B is to the left of C, so FB, and right is FC. So again, so I'm following the convention, writing left on the top and right on the bottom. Obviously, to do it the other way should be the same, okay, conceptually. And that's why if this product of ratios is something, it should be 1, right? And so it is 1, no doubt. Do we need to prove this? No, right? Because you can just use the Ceva's theorem, right? So I'm not proving this, but you can just use the Ceva's theorem, because you can say, okay, I'll draw this line and then I will draw this thing, right? And I will, I have this ratio, FB, FC, these ratios. I can find this ratio, then I can find the area of the triangles, and then I can find AO by OB, right? In terms of the other ratios, right? And the product will be 1. Okay, it will take some calculations to do. I'm not giving it as a homework. Let's leave that. Okay, but the point is that it is no new idea is needed to prove this result. Okay, there's nothing new about this. Okay, I mean, you could do this in other ways also, right? I mean, if you want to find AO, basically we have all the techniques. We are now just making, we are now just making theorems out of those techniques. What is the other way? Well, the other way is to just draw a line parallel to this, right? We have already done this thing several times. We have done it. We have basically proved Menelaus theorem and Ceva's theorem in the hard ways. Okay, in special situations, not special actually, in just computational when numbers are there. You can do this, right? And then you can write, okay, AO by OB is, you can put a point D. Okay. So do you guys see how you could do this problem? I mean, how you could prove this result? Basically, Ceva's theorem also we proved with our own ideas, which we had developed earlier. Yeah. So this also you can just do in the same way. Okay. Like you can say, okay, AO by OD is AE by ED, but then ED by DC is this by this, and some jugglery with the ratios you can do, and you can do it. Please do it. Okay, I want one of you at least to do it, write it, or say it next time. Okay, because it is very similar to how we proved Ceva's theorem, and since we have already proved it on our own, our own proof, I have full faith that you guys can do this. Try to do this also. You just need a bit patience. You can look at how we did that proof, Ceva's theorem also. Basically, we have shown 2 ways to do it. In the books, you will usually see, there are other proofs using perpendiculars and so on. Fine, we are okay with this. This is called the Menelaus theorem. Very important. These are the 2 pillars. Okay, kind of. Okay. Well, there is other side of the theorem, which we'll not see now. See that later, because I want to first prove concurrency and collinearity with just bare hands. Because you see, what we did earlier is we found these ratios and areas in these kind of questions without using the theorems. And so now we understand the theorems and we also kind of see that we can prove them. Okay. The converse of these theorems help you to show collinearity and concurrency from the ratios. They say that if this ratio is satisfied, then these 3 points have to be on the same line. Those things. Similarly for concurrency in Ceva's theorem. But if I just do the proof now, you will understand and so on. But first, we should be able to prove some collinearities and concurrencies on our own, right? Without using any results. Then we can appreciate these and kind of even foresee how to do them. And half the job is already done. It will be much easier. So let's go there. And actually, the next problem I had given, I think, was related to this. But I would like to hear the problem from one of you first. Maybe Shana, you can say if you have the problems. What was the next problem you would like? Oh, sorry, 1 minute. 1 minute. I read this. Okay, now. Yes, so we had ABC. Okay. Okay. Yes. So something like this. Okay. One of them was parallel, right? So maybe I first write ABC, then you can tell me. So where is X? Oh, like this. Okay. Right. Okay. So all of them are not parallel. It may look like that the way I've drawn it. But let me just actually change it. Otherwise, it can just lead to misinterpretation. So let me change it. Just change a little bit. You see, if I make one of them non-parallel, then the next one also becomes non-parallel. One of them is parallel, and I make a second one non-parallel. The third one also becomes non-parallel. I kind of ask you to prove this in the next exercise. We'll see. But either ways, let's continue this. Oh yes, so we have to extend them. So let's extend it like this only. Yeah. Mm-hmm. Mm-hmm. Oh yeah. That also I need to do. So let's do. Right. So one doesn't need to draw the whole picture at once if it's confusing, but I'm drawing it because maybe you guys should have tried the question, but if there is, we'll do it. D, E, F. Okay. Okay, so that ratio I've given, okay. 8 by. So this is 8 by 7. Okay, and then I want to find xi by iy. Okay, okay. Ishan, why is your microphone having so much other noise? Is it some? Do you also hear it? No. Okay, okay. Yeah, there is a. Yeah, I mean, it's not a problem at all for me, but yeah, it's a little bit of. Yeah, maybe. No, no, no. It is always. It's mostly always like that. I mean, your voice is clear, but there is some extra background. Maybe are you maybe not using a your earphone? Maybe something like that. Something. Yeah, it's okay. It's not a problem, but yeah. Okay. Anyways, let's do this. Let's do this. Okay. Let's see. So this is like, Ceva's theorem will help you a little bit, but then, you need other things. Let's see. So maybe I can just say application of Ceva's theorem. Just think I'll drink some water. So did you guys try these problems? Sorry, did you guys try these problems? This one? Oh, no, that would be too easy. Okay. Pragdish, could you make progress in this one? It's slightly tricky, maybe. Okay. So I'd given this two classes back, but that's not a problem. So let me then give a hint, okay? Because now I want to be able to do this one. So what do you think should be YG by GZ? So you guys tell me this first. Pragdish, do you see it? Okay. So this is also one. This we have seen, right? If you take this triangle and parallel, and this ratio is same. That ratio doesn't change. So this now I would say we are done almost. So we have YG by GZ, and you have XH by HZ. Yeah, right. So as Ishana is saying, so we have XYZ, and you can see, right? ZI, YH, and XG, these are the lines which are concurrent, and so same Ceva's theorem you can apply, right? So you can just apply it. You should get XI by IY. What is it coming out to be? Is it 8 by 7 or 7 by 8 something? It shouldn't be. Should it be 8 by 7 or 7 by 8? Oh, no, you're right. You're right. Yeah. Right. It should be 8 by 7. Yeah. So you can apply Ceva's theorem, or in fact, we have actually already done this problem, right? We know that if this is the midpoint, then this is parallel. This we have also seen earlier, but you can do it just applying the theorem also. Okay. So is it clear to both of you? Like, so you can just apply this theorem. I mean, already Shana has told me the answer. So you see this HZ by XH. So Pragdish, is it okay? Just applying this result, this is equal to 1, and you can find it is just simple. But yeah, and you see the strategy is clear. I mean, I just made this problem up while obviously I would have seen similar problem earlier. That's why, but yeah. Okay, so this is simple. Now we want to do problems in which we prove concurrency. So far we are using concurrency. Very good. Okay, we are using concurrency in this way. I mean, we could do all this from scratch all the time, right? We can always, when you want xi by y, iy, you can always draw this parallel line, do a lot of calculations, and then get. But now we have put all those calculations into a theorem. So I want you guys to appreciate theorems. Okay, theorems are these abstractions of methods. When just arranged, when the methods are kind of done in general for general variables, and then what you end up getting can be applied for in any situation or large number of situations. That's what a theorem becomes. And so theorems are just like that. They are not some sudden thing that someone suddenly comes up with overnight, or just suddenly, right? It just comes through these calculations and observations, or some numbers it comes, and then you obviously this is not always the case, but you can see like in these things, it is like that's one way to understand these things and remember these things, and have a feeling for these things. Okay. So let's go to the next question. I think next question was about, let me say the next question, the version I'm interested in right now. I may be missing one or two questions, but those will be similar to this. What I want to do is I've taken this triangle. Now I'm taking a parallel triangle. Okay. Taking a triangle parallel to this. I could take this outside the triangle also, but I'm just taking it inside for now. So it's a parallel triangle. And I remember I had seen this in, so there is a book by Geometry, there's a book called Geometry Revisited, which may be a little advanced for you guys now. Geometry Revisited by Coxeter. So I remember this was the kind of first serious book I read in Euclidean geometry. Yeah, I think I read it quite late. I mean, I didn't have teachers and I didn't know things when I was in grade 9, okay, anything. I read this in class 12, I think. This is a very good book. And I think this has had this kind of stuck. And I was so excited with this book. I got a hard copy of this, or no, soft copy. So in those days, getting a soft copy of a book was like, oh, how did I get a soft copy? I mean, I didn't know that such things exist. Okay. So I got it and I was so excited. I just read like 70, 80 pages in one day. Obviously, I didn't absorb all of them, but I just kept reading all day and the night. And because I was like, oh, okay, the PDFs also exist. I used to think they should buy all the books. I didn't know these things. And then obviously nowadays it's everywhere. These things are there, but yeah, there's another book called Introduction to Geometry. Now, I think you guys will not have the time to read these things because there are. I mean, I was a bad student, so I didn't really study other things, so it was okay for me maybe. But yeah, Introduction to Geometry by the same author. He's a master. He's really a master of geometry. He has written some other like college level geometry books. So these are like high school level, and obviously this is the advanced. But yeah, Introduction to Geometry by Coxeter Dragon. It's a classical type book. It's not like present books where you'll quickly get theorems and Olympiad problems. But the way he does it is just awesome. Okay. And there's a natural flow of things. Okay. Obviously, it's not too verbal like me because it has to be in a book, right? So he has to say things concisely. But still, he's a master. See. So you can read this book if you want. Okay. But these days, we just Google things and it just comes up. So we don't read books really nowadays. But I mean, students these days. But you can try to read. It's a very good read. And you can also buy soft copy, hard copy. It's not too costly, I think. But yeah, like it's much better than the Indian books that I know. I mean, nothing against Indian books, but this book in particular is very good. This one, and so this one should also be. I've not read this one. Like it's better than the Challenges and Thrills, which you may have heard, and other Indian books. And these are at the right level. They're not very advanced. So Coxeter is a very, a very good mathematician, great mathematician. And there are a lot of theorems named after him. So kind of seen this there and it stuck with me. So this was the first thing I actually proved that 3 lines are concurrent, I think. So what we want to show now is, so obviously this is a parallel, no doubt. All parallel, everything parallel. Yeah, they want to show that. So show that AA prime, BB prime, and CC prime are concurrent. They pass through the same point, which is like not at all hard to believe, right? It's just almost like obvious, but how do we prove it? Because you may have never proved that some things are concurrent. It's a new kind of thing to prove, to see maybe it's intuitive and so on. Mm-hmm. Uh, but that we have not proved, right? That the ratio implies concurrency. The ratio being 1 implying concurrency, we have not proved that. Right, so we cannot really, let's not use it. Okay. Yeah, and also it's not very clear. It's a vague idea still. So let's try to do this directly. Let's not use any results. How do you ever prove that 3 lines pass through the same point? It's a very strange thing to prove if you think about it. To prove. So don't you guys feel that it's almost like impossible to prove that something's a concurrent? Doesn't it feel strange? And actually, like if you take, so if you take two, like if you take two of them and they pass through the point, how do you show that the third one passes through that point? That's a very strange thing to prove. Yeah, I mean, it seems true, but it's strange. And you can feel like anytime if you ask yourself to prove these things are concurrent, it just becomes a very strange question. Like it's a different type of thing again, right? It seems. And, how do you prove that this will pass through this? I mean, like you can say, I can see it passes, but how do you prove it? It's very strange. So you see, you can never prove such things directly. It's impossible. The kind of statement it is, you cannot prove that this passes through this. What you can, yes, yeah, in the sense, yeah, here because the nature of the thing is that we are not producing an object in the end in this kind of statements, right? In that sense, it is easy, and also because it's obvious. We are not, so in the end, we are not producing an object, right? Usually when you're, I told you ask the find the area, prove that the area is this, but in the end, you're basically finding the area, right? You're finding something, you're finding some ratio, you're finding something, right? So that is like so you do some steps and then you find something, so that makes it fine. But if I show proof this is a concurrent, you're not really going to get anything in the end. If you start some steps and you're not going to get an object in the end or some number or anything. So that's why it's a strange statement. So such statements have to be done by contradiction. Okay, kind of have to be done by contradiction. Okay, like if I give you like, just if I ask you something like this, if I give you, this is again a very obvious statement, but again, I mean, it's not hard to prove in the sense, but it's just that a different way is needed to prove that. Okay, it's like if I tell you that this is the median and this is the median, if I tell you that prove that all the 3 medians pass through the same point, how are you going to do it? You'll say, okay, I'll take this median and I'll take this median. But how do I show that this median passes through this? Very strange, right? You can say, okay, let's assume it does not pass through it. Something like that, right? This is a vague thing. I'm not asking you to prove it right now. Okay. I'm saying that if you want to show that the 3 medians are concurrent, then you cannot directly show such a thing. You can do something like this. You can say, okay, that these two things, there will be these two medians pass through this point. I want to show that the third median also passes through the point. Okay, let me write this last thing. So want to show, I mean, you guys agree these two are median. I mean, I'm not writing everything. So you want to show that third median passes through G. But can't show, right? What you will do is you will say, okay, let there be a pink line which passes through G. Okay. You create a phantom line. This is called phantom line, but this is just word. You will say, let there be a third line which passes through G. Okay, let CT be the line that passes through G. Then what do you want? Then what would you show? You will show, you say, I will show that T is the midpoint. Right? And then you will be like, okay, then this is the median. Okay, because I cannot draw two medians from C, right? Pragadesh, do you see the idea? It's like a different way to do things. Right? So yeah, so I'm not directly like drawing the median and showing that it passes through the point. I'm saying that if there is another line, if there is some line that passes through it, it is a median. But there is no other median. There's only one median. Okay. And so the median has to be this. Or formally you have to say, okay, let the median not pass through it. Let this be some other line which passes through it. Then this ratio is 1. But this ratio is also 1. And so this T and M have to be same. And so you can, yeah. I mean, that's a formal way. Otherwise, yeah, formal. But you understand. Things like this have to be done like that. So this homework, and now homework, show that the three medians pass the same point. Show, this is very not difficult, but okay. Show that medians are concurrent. And remember, I'm not really directly applying Ceva's theorem. You may apply what we have proved. Don't apply what we have not proved, like the converse of it. Okay. Though it's all simple now, but are concurrent. And also show that, so let me see, what other easy things can we ask? I don't know what altitude, so that is easy. So let me not ask that. Angle bisectors, you guys should try. Yeah, angle bisectors. Angle bisectors, you guys know. If you don't know, you tell me. Angle bisectors are concurrent. I will do this problem, but just giving this quickly. Do these two. Okay, do these two, and then you can see. So you can note it down now or later, whatever. So I've kind of told you the technique. First we realize it, then we. This is the question. Now let us do this question. So again, how are we going to do this question? So once again, you take the two of them and you take their intersection point. You want to show that this line through CC prime passes through this. That's what you want to show. How do you show it? So that's what you want to show, right? That the line through CC prime passes through that intersection point. So want to show, so I'll just end. Okay, I'll just end in 5 minutes. So just, oh, it's already 10:50. So but just give me 5 minutes maybe. Want to show C prime passes through P. How do you show it? Hmm.
Basically, CC prime does not pass through P, triangle cannot be parallel.
If CC prime does not pass through P, then the triangle cannot be parallel.
It doesn't pass through P, A prime, C prime cannot
Yes, right. So I basically say that formally. Okay. Yeah, essentially that's what I have in mind. So what I'll do is I'll basically prove that. Let's say that. So we have, so this one doesn't need the other two, right? So let's say that P is the point of the other two, and I'll say that, okay, I will join P with C. Okay, I'll join P with C. Just like, I drew the median, third median. I've joined P with C. And then I will say, I join P with C, I'll say, okay, now you take a line through this, which is parallel. Okay. And then I will say, now you will see that the third line will also be parallel. And those are easy to prove. They're just ratios. Okay. So I'm saying I'm drawing this line B prime C prime parallel to B C. Then I will say you look at the third one, A prime C prime, that will also be parallel. So now we know that. Okay. So I'm saying that basically if there is a line that passes, the line from P to C, okay, if I join that line, and if two of the sides are parallel, and the third is also parallel, that is the property of this line. Okay. Okay, it's a little confusing to say. So that is the property of this line. Yes, and so if so basically that means that the line through C prime has to pass through P, because there is a unique line through C prime. Right? Yeah. Yes, right. So, well, what am I doing? So we wanted to say that. So let's make it so that it is not passing through it. Okay. So if I somehow take the line, that's by contradiction is the most straightforward way. So if I say that I take this line and it is not passing through the intersection points. Okay, let's say it's not passing through. Okay. Now I will say, now you take this line that is kind of, so you take this line and you join it with C. It's a very strange thing, but what to do? Okay. You take this line and you join it with C. But don't worry, these are the things which only prove once in life. And then we make a theorem out of it. We will do that. It's called some homothety thing, but let's do this first. Getting confused. Yeah, because this is like that. Okay, so I have to draw some sort of a pseudo. Okay, let's do the pseudo line thing. Okay, so yeah, so let's assume that the line that is passing from P is not passing through C. Okay, okay, but then this line PC. Okay, so you understand what P is, right? So I've assumed that that line which we were supposed to prove passes through P is not passing through P, so that's outside in different place. Now we took a line which from P which we joined it with C, like we joined on the median. Now we will show that this PC has the same properties as CC prime. How do we show that? We will say, okay, you take from B prime, C prime, extend it to make this parallel. Extend this parallel line, right? Maybe I'll just say this next time again. Extend this parallel line. Okay, just a bit more carefully. Okay, extend this parallel line. Then this has to also be parallel. Right. Yeah. So I'm extending B prime, C prime. Okay, I'm extending B prime, C prime. So see, the goal is to try to show that this PC has the same properties as CC prime, because we know that they are all the same lines in the end. Right. So see, I wanted to show that CC prime, the line, if I join from CC prime, I wanted to show that actually passes through P, right? This is what I wanted to show. But I have to go by contradiction because I cannot do it directly. So I assume it doesn't pass. So let it go somewhere else. Okay, I don't even need to draw this somewhere else thing, but just to emphasize that, let's just draw it like this only. So let's say that this CC prime passes through somewhere else. It doesn't pass through P, which means that this PC is not passing through C, not passing through C prime. They are all the same statements, right? So PC is not passing through CC prime. I want to show this is not true. Is it clear till here? Okay. So I wanted to show that CC prime passes through P, but I'm assuming, let's say, it doesn't pass. So it means that PC is not the line CC prime. They are different lines. Okay. But I will show that they are the same lines. How I will show? By showing that it has the same properties like CC prime. But how will I mirror the properties? By mirroring the situation. Mirroring the situation means that I'll extend this B prime, C prime, and it hits at this pink point. Okay, you can call it C double prime or whatever. Okay. Let's say C double prime. But then what will I do? I will join from A to this. I'm trying to mirror the situation. I'm trying to show that C prime and C double prime and C prime are same basically in the end, right? So I'll mirror the situation, right? So I'll join this A prime, A prime and C double prime, A prime and this pink point. But then A prime and this pink point has to be parallel to AC. Is that right? A prime and C double prime has to be parallel to AC. Because again, two sides are parallel, right? If you just forget about this in a second, it has to be parallel, okay? I'll say this again next time, but you get the idea. So this is parallel, but what does that mean? I mean, this is also parallel to A prime, C prime, because they all three are parallel. But then how is that possible? From one point, you can only get one parallel line, right? Parallel to some AC. Parallel to AC, you can only get one such parallel line, right? From one point A prime. That's yeah, C double prime. That's the axiom of one of the axioms of Euclid, right? That from one parallel line, I mean that's true, but what does truth mean in mathematics? Three axioms. So there's only one parallel, and we're using that. So this becomes the same. So you see, I mean, only if we assume that it is not possible, then we get something to start with. Right? Then we can actually use the point P to get started. Is that right? If we assume that it is not passing through, then we can actually get started. Okay. Then we get started, and then we show some contradiction by this way. CC prime or TT prime on the base of the triangle. In this case, this was enough. Okay. Yeah. So maybe you can just go over this once again if you need, Pragadish, you also. But I will try to say this next time. But just go over this once again if possible. Or just think about it, and I will explain this next time again, because this was a little tricky than I had expected. Okay. But then I just want you guys to do this if you have okay, but otherwise I'll do this next time again. What I'm saying is I'm just going to take this outside the triangle. And the lines are parallel. So you understand this is parallel. Now doesn't look parallel, but just assume it. Forgive the diagram. So if two of them are parallel, show that the third is parallel, and that will follow. So I'm not giving that. Now I want you to show that this line and this line, I mean, maybe not that direction, but maybe this direction. These three are going to concur. Sorry. Yeah, so try to show that they are concurrent. It's actually not true, but there is an exception. But either these three will also be parallel, or they will be concurrent. You see the similarity, right? I have two parallel triangles. In this case, it was one inside the other. But I'm saying that you can just do this in any situation. And when you join the corresponding vertices, they are concurrent. If they're not concurrent, they are parallel. They are parallel means they are concurrent at infinity. Okay. So try to do this. It's a very similar question. Just same ideas will work, you know. So take two of them and third one doesn't pass through that and so on. That will be a test of whether you have understood this. Otherwise, we will do this next time. Okay. But these problems, surely try these ones which I've given. These are doable. Okay. So let's meet next time. It's already pretty late. I'll try to end on time next time. I'll start on time and end on time. Okay. Thank you.